Picture this. You're doing your normal morning routine. You wake up, stretch, walk over to the window, and open the blinds, completely expecting the gentle, familiar warmth of the morning sun. But instead of that comforting yellow glow, you are instantly hit by a blinding, terrifyingly intense blue-white light. A literal cinematic cosmic event is unfolding right outside your window.
Welcome to This Explainer. Today, we are diving headfirst into a mind-bending what-if scenario. What if our stable, perfectly mundane yellow sun was instantaneously replaced by a massive blue star? Specifically, a blue supergiant sitting in the exact same position in the center of our solar system.
I mean, just imagine this inconceivable dawn. It's gorgeous, right? But honestly, it is also absolutely terrifying. If this actually happened, it wouldn't just be some cool optical illusion or a weird trick of our atmosphere. It wouldn't just be our sun with an Instagram filter over it. This would mean a fundamental, profound, and exceptionally dangerous change in the heart of our solar system. The literal laws of physics in our cosmic neighborhood would be violently rewritten in a single instant.
Section 1. Why are stars blue? Heat dictates a star's color, but let's actually look at why some stars are blue in the first place, and what that actually tells us about them.
When you put our everyday sun next to massive O and B-type supergiants, the difference is just staggering. In astrophysics, heat is what determines color. Think about a flame. The hottest part of the fire is blue, right? While the hottest stars in the universe are exactly the same, they're blue-white. While our sun sits at a relatively cool 5,700 Kelvin, these massive giants are out there burning at extreme temperatures, ranging anywhere from 10,000 to well over 40,000 Kelvin.
And when you actually look at the numbers, the sheer scale is honestly horrifying. Let's use our sun as a baseline. 1 solar radius, 1 times the luminosity. A typical blue supergiant completely dwarfs it. We're talking 20 to over 200 times wider, with a luminosity that can be up to 1 million times greater. These aren't just stars, they are absolute cosmic engines of extreme energy.
So, you're probably wondering, would this giant star just instantly swallow the Earth physically? Let's bust that myth right now. The Earth sits about 215 solar radii away from the Sun. Even a massive blue supergiant like Deneb, which is about 203 solar radii wide, would expand out and absolutely vaporize Mercury and Venus, but its physical surface would actually stop just short of Earth's orbit. Now, this is very different from a red supergiant like Betelgeuse, which easily inflates enough to just gulp us down. The real terror of a blue supergiant doesn't come from its physical volume, it comes from its blinding brightness and heat.
Section 2. Disastrous heat and radiation. Just because we aren't physically swallowed by the star's plasma doesn't mean we're safe, not by a long shot. We would face immediate, fatal, physical consequences down here on the ground.
82 million watts. Okay, to put that in perspective, right now, every square meter of Earth receives a nice, manageable 1,361 watts of solar energy. But if our sun became even a modest blue supergiant, Earth would get blasted with a horrifying 82 million watts per square meter. Our planet's climate would literally shatter instantly, because we'd be getting hit with more energy than the actual surface of our current sun emits.
The immediate aftermath of all that energy: visceral. This impossible heat would trigger a catastrophic runaway greenhouse effect on steroids. The oceans wouldn't just gradually warm up like a hot tub, they would rapidly boil and evaporate entirely into the atmosphere in a matter of minutes. Earth's surface would instantly transform into a sterilized, molten wasteland. But hey, space is about way more than just raw heat. We'd also be facing a relentless, invisible cosmic assault. You see, a blue supergiant shifts its energy output massively into ultraviolet and X-ray radiation. This aggressive UV light would instantly shred Earth's ozone layer, ionizing molecules and completely destroying the very chemical bonds required for complex life. On top of that, you've got massive stellar winds blowing at 2,500 kilometers per second. Those winds would violently strip away whatever was left of our atmosphere and totally obliterate our protective magnetosphere.
Section 3. The Lost Habitable Zone. Okay, so Earth is obviously completely lost in this scenario. But where would a planet actually need to be to survive this furious new star? First, let's lock down a really crucial concept: the habitable zone. This is the specific orbital region around a star where a planet receives exactly the right amount of energy to maintain liquid water on its surface. You've probably heard it called the Goldilocks zone.
The big takeaway here is that this safe zone is completely 100% dependent on the star's total energy output.
And because of that intense heat we just talked about, the safe zone gets violently shoved away. The immense luminosity of the blue star forces that life-friendly ring impossibly far away from where Earth currently orbits, leaving us deep, deep in the scorching danger zone. To survive, a planet would literally have to orbit way out into the outer solar system, pushed back by the sheer radiative force of the blue supergiant.
Section 4. Time runs out fast. Now, let's just pretend for a second that we actually have a rocky planet perfectly positioned out there in that distant new habitable zone. Are we safe? Well, no. Because in astrophysics, massive mass equals a severely shortened lifespan. When you look at the timeline of a star's life, the contrast is just wild. It perfectly juxtaposes the 10 billion-year marathon of our stable yellow sun against the frantic, exhausting sprint of a blue star. Because a massive blue supergiant has so much gravity and crushing pressure in its core, it burns through its nuclear fuel at blinding speeds. Its entire lifespan? It can be just a few million years. The clock simply runs out way too fast. I mean, remember, it took hundreds of millions of years just for the absolute simplest life to form here on Earth, and billions of years for complex life to finally evolve. Even if a planet was perfectly placed in our new blue star's distant habitable zone, the star would die millions of years before complex biology could ever even hope to take hold. It is a spectacularly beautiful, but entirely hostile environment for evolution.
Section 5. The cosmic end supernova. And that incredibly short lifespan, yeah, it builds up to a grand, catastrophic finale, the inevitable death of a massive star.
So, when a massive blue star exhausts its nuclear fuel, it can no longer generate the outward pressure it needs to fight off its own immense gravity. The core collapses in on itself in literally a fraction of a second. And boom, the outer layers detonate. This is a core collapse supernova, easily one of the most violent events in the entire universe. And this isn't just theory, by the way. Back in 1987, a blue supergiant named Sandelek-69202 actually exploded exactly like this. It became supernova 1987A, totally shocking astronomers who originally thought only red supergiants met this kind of fate.
The aftermath of this explosion is total cosmic devastation. Heavy elements get violently blasted out into interstellar space, and the crushed core turns into either a superdense neutron star or a black hole. Now, supernova 1987A was safely 168,000 light-years away from us, but in our scenario, the distance from the supernova to Earth is exactly 0. It's happening right in the center of our solar system. Contrast that with our real sun, which is eventually just going to undergo a gentle expansion into a red giant and peacefully puff away its outer layers into a beautiful planetary nebula, leaving behind a quiet little white dwarf. So, while a distant, peaceful-looking alien world orbiting a massive blue star might seem incredibly cinematic and cool, the reality is that it's a super fragile, impossibly hostile environment. It really forces us to stop and reflect on the highly specific, almost perfect parameters required for our own existence.
This completely flips the script, doesn't it? It turns an apocalyptic what-if scenario into a profound celebration of our quiet, unassuming solar system. The sheer fact that you and I are here, communicating, evolving, and able to even ask this what-if question is the ultimate proof. A boring yellow star is exactly what is needed for us to exist.
So, the next time you step outside and complain that the weather is a little too hot, just remember that the sun up there isn't boiling the oceans in seconds or blowing away our atmosphere. It's giving us the perfect, gentle balance of heat, light, and most importantly, time. Aren't you glad we orbit a boring yellow dwarf? Thank you for joining me for this explainer, and hey, never stop looking up.